In this video, I'll go through hypothesis testing for the mean in the case of a known assumed population standard deviation. So our example here is 36 sample measurements of weights of coffee, and the hypothesized mean is 3 pounds, and we're testing a lower tail test where the null hypothesis is that the mean is greater than or equal to 3, and the alternative hypothesis is that the mean is less than 3. Our assumed population standard deviation is 0.18, sample size is 36, and so our standard error, as usual, standard deviation divided by the square root of n. Our sample mean from the data comes to 2.92, and then here's our hypothesized mean. Our Z statistic, and we can use a Z statistic in this case because we're assuming the population standard deviation is known, so we can use a normal distribution, and this is equal to the sample mean minus the hypothesized mean, all divided by the standard error, and that comes to minus 2.67. And then the p-value, because we're doing a lower tail test, that means that the p-value is the left-hand tail area beyond the test statistic. So to calculate that, we can use norm.dist, and the first argument is the Z statistic, and then second argument is the mean, which is 0 for a standard normal distribution. Standard deviation is 1. And then true means that we're looking at the cumulative distribution. And so that tells us that the left-hand tail area to the left of minus 2.67 comes to 0.0038. And that's our p-value for a lower tail test. This test is using a significance level of 0.01. This was determined before looking at the data. And so our decision is if the p-value is less than the significance level, then we reject the null hypothesis. So I've set that up here in this if statement. If the p-value is less than alpha, then reject the null, otherwise do not reject the null. And in this case, 0.0038 is less than 0.01, so we reject the null. Another way of doing this is to use a critical value, and for this we find the value of a standard normal random variable that would give us a left-hand tail area, a lower tail area of 0.01, and that number is minus 2.33, and because we're doing a lower tail test, the decision is to reject the null hypothesis if our Z statistic is to the left of that critical value. And again, we get the same outcome because it's equivalent. Whether you use the Z critical value or the p-value, you'll end up making the same decision. Let's see how to do this using XLStat. So if we select parametric tests, one sample Z test, and then we select our data. We select Z-test for the option down here where it says tests. Under options, let's do a lower tail test. So less than is in the alternative hypothesis. We'll type our hypothesized mean in here. So that's 3. We'll set a significance level of 1%. And then we'll use a user-defined variance. And with a standard deviation of 0.18, if we square that, we get 0.0324. So that's our variance. So type 0.0324 in here. And then under outputs, we'll just do the detailed results. Okay, that. It does its calculating. And then once it displays, we'll see if we get the same results we got by hand. So we got a test statistic of minus 2.67, I think it was, and a p-value of 0.0038. So when XLStat does it, there's our test statistic, minus 2.67. There's our critical value, minus 2.326. So if our test statistic is to the left of that, which it is, then we reject the null hypothesis. Alternatively, here's our p-value, 0.004. You can actually see up here it's 0.0038 if you use 4 decimal places. That's what we calculated before. And there's our alpha. So if our p-value is less than our alpha, then we reject the null hypothesis. What would this look like if we did a two-tailed test instead? So if we did a two-tailed test, a lot of the information is the same. Standard deviation is the same, sample size, standard error, test statistic. Sorry, sample mean, hypothesized mean, test statistic. All of those numbers are the same as we had for the lower tail test. The first number that differs is the p-value. So because we're doing a two-tail test, the p-value is now not only the left-hand tail area to the left of minus 2.67, but we add to that the right tail area to the right of plus 2.67. And we already know that the left tail area was 0.0038. And because the normal distribution is symmetric about 0, the two-tail p-value must be twice as big as that. Okay, so 0.0077 for the p-value. Alpha's the same. We're still testing at a 1% significance level, and the decision rule is the same. If the p-value is less than alpha, then reject the null hypothesis, which it is in this case. If you're using the critical value, then what differs here is we have our significance level 0.01, but because we're doing a two-tail test, we put half of that probability in one tail and half in the other tail. So if you look at the formula here, that's why I've got that we're putting alpha divided by 2 and finding the tail area to the not the tail area, we're finding the Z critical value that will have a probability of 0.01 divided by 2, so 0.005 in the left tail. And that critical value is minus 2.58. It's further away from 0 because there's a smaller tail area associated with it. Decision rule is the same. If the test statistic is to the left of that critical value, then reject the null hypothesis. And it is in this case, so we reject the null. How about an Uppertailed test? So let's look at a different data set. This is, what is this? Looks like something to do with golf. So it's a golf ball with a mean driving distance, supposed to have a mean driving distance of 295 yards. Okay, and we've got some data to test that. We're assuming a standard deviation, population standard deviation of 12. We've got 50 sample measurements, standard error, standard deviation divided by square root of n. The sample mean from the data comes to 297.6, and our hypothesized mean is 295. Z statistic is sample mean minus hypothesized mean divided by standard error. And we're doing an Uppertailed test, so our p-value will be the upper tail area to the right of the Z statistic. And the way that we calculate this in Excel is if we use norm.dist with the test statistic as the first argument, that will give the area to the left of the Z statistic. So the tail area to the right of the test statistic will be 1 minus that. So the p-value comes to 0.0628. We're going to do a significance level of 0.05 for this test. Our decision rule is the same as it always is. If the p-value is less than alpha, reject the null. It's not in this case, it's bigger than alpha, so we do not reject the null hypothesis in this case. Okay, and so we could conclude that the alternative hypothesis seems to be a better bet here. Okay, that the mean is bigger than 295. If we're using a critical value approach, we're working with the Uppertailed here because we're doing an Uppertailed test. So our critical value is going to be the value of a normal random variable, standard normal random variable that has a tail area of 0.05 in the upper tail. So the way we calculate that is if I do 1 minus alpha, that will give me 0.95, and then norm.inv tells me the value of z that would have an area of 0.95 to the left of it. So that will give me my critical value. Decision rule is the same as it was before. It's not quite the same as before because we're doing an Uppertailed test. So this time it's if the Z statistic is in the upper rejection region, so to the right of the critical value. And 1.53 is not in the rejection region. It's not bigger than 1.64. So we do not reject the null hypothesis. And then let's see how to do that in Excel stat. So parametric tests, one sample Z test. We'll select the data. So the data in this case is going to be so that didn't work. Sorry, let's try that again. I'm picking the golf data. Here we go. Okay, that's better. We'll do a Z test. Our options, we'll do an Uppertailed test. Theoretical mean was, 295? And the variance, what we were using for the variance. Well, for the standard deviation, we had 12, so the variance must be 144. 12 squared. And we're doing a 5% significance level. Okay, hopefully that's all set up correctly. Let's see if we got the same answers as before when we did it by hand. So our test statistic, 1.532. Yeah, that's what we got before. And our critical value, 1.645. Yeah. Our p-value, 0.063. Yeah, that matches with what we got before. Okay, and alpha 0.05. And in this case, we're failing to reject the null hypothesis. Okay, and it tells us this down here. We cannot reject the null hypothesis. Okay, and just to finish up, if you were to do a two-tailed test here, okay, remember these numbers are the same all the way up to the Z statistic. The p-value now, because we're doing a two-tailed test, is going to be 2 times the Uppertailed p-value, because now we have to consider not just the tail area in the upper tail, but the tail area in the lower tail. And so if we double 0.0628, we get 0.1255. Decision rule is the same. Okay, if the p-value is bigger than the significance level, which it is in this case, then we fail to reject the null hypothesis. For the critical value, this should be a familiar number to you. Now we're putting our significance level half in the lower tail, half in the upper tail. And if we do that, if we put 0.025 in the upper tail, we get a critical value of 1.96. Decision rule is if the test statistic is to the right of our critical value, then reject the null hypothesis. It's not in this case, so we fail to reject the null hypothesis.